So let's continue our discussion about climate and change of climate and things like that we started in the last lecture. And the last point we started to discuss is this global warming problem that people believe, climate scientists, let's say 95% of climate scientists believe that these two curves, the CO2 change curve and the global mean temperatures are related to each other. There's a minority of climate scientists who believe that maybe this could be related to other things, like, for example, we mentioned also in the last lecture, solar radiation is a very important input. So if that's varying, that will have a very strong impact on the global climate, obviously. And some people believe, yeah, it could be due to that. But let's say 95%, including me, believe that these two curves are related. And not only because these two curves are correlated. That's not, for this short period, would you believe that this is a proof, just to see that two curves are kind of correlated? Do you believe that this could be taken as a proof for a scientific relationship? Obviously not. You're all physicists. You could plot any increasing curve in here, maybe some stock market curve or birth rate or something like this of animals, whatever. Anything that is increasing will be positively correlated with the mean temperature curve. So that's obviously not a proof. So of course, we need a physical understanding of why these two curves should be related. But before doing that, people have taken, or let's say in parallel, and we will look at this first, have used another technique to try to understand if these two curves may be in fact related. So one possibility is to try to get more data. So it's obvious that here we have 130 years of data, and that's not enough to find a relationship between the two, because both just somehow increase, and that cannot be taken as any statistical proof that they are really related. So what people have tried to do is to go back in the past. Now that's very difficult because we have no observations going back before let's say 1850. There are almost no temperature observations anymore, not even in Europe. People have started in the 1900s to make really observations of temperature even in Europe. So before that, there's no observational record of temperature. So what can we do? People have been thinking a lot. What can we do? One very simple thing that you may know of is to use another technique, which is, for example, trees. Look at trees. Cut a very old tree, and look at the tree rings. The thickness of the ring gives you information about the climate that has been going on in a particular year. So you know which year we have now, so you can count back. Every ring is 1 year. You can go and count back in the past. Maybe an old tree can have up to a few thousands of years. So you can go back a few thousands of years and estimate from this thickness of each ring if the climate in that particular location, in that particular year, was perhaps wet or dry, for example. Then in wet years, maybe the tree has a lot of water available to grow. But there are other factors, of course, that influences temperature, and maybe some other factors can influence. So it's a very tricky thing to do these estimates. But tree ring is one possibility. But it leads us back only perhaps a few thousand years. And maybe even looking at these two curves, they are so smooth that maybe even a few thousand years is not enough to find a robust correlation. So there are other methods. And the one very famous method is to go to the Antarctica, for example, and dig a hole into the ice sheet. So the ice sheet in the Antarctica is millions of years old. And if you dig down into the to the ice. So each year the ice is layered, and in the ground it melts. On top it accumulates, and if you go essentially down, drilling down, you go into the past of the history of the Earth. And so people dig out huge tubes of ice, but that's not yet enough. Maybe going down gives you information, yeah, if you go down, then this ice has a certain age. But how do I estimate at what age, at what time in the past, what temperature may have been, or what climate may have been in this region? And so there are techniques. The technique is that ice typically contains small bubbles of air. And from the constitution of this air, scientists, I'm really not an expert of this, but scientists are able to estimate what was the temperature, the annual average temperature in that particular location. It's a very complicated mechanism. And in this way, here's an example where people have digged from the Antarctica. Vostok ice core is very famous of these. We call this proxy data because it's not a measurement. One has to be very careful to interpret this data because it can have big errors. But the more information people find all over the world, the more we can be confident with what we have as information. So this is not the only information. There are correlates which can be used also in other information. But this is a very famous series. And what you see here on this graph is time going back here in the past for, in this case, 400,000 years. So that's now a different time scale from what we have been looking at before. And this, the curve that you see here is the CO2 concentration, and we measure this in parts per million of volume content. Anyway, what you see at the moment, we are probably more than 300 of these parts per million, and it's a relatively high concentration. But we are, well, that's our current situation. The last time there seems to be this very strong increase, but probably in this graph you wouldn't even see the CO2 increase in the last 100 years very well because the time scale is so squeezed. As you can see, like one small dig here is already 10,000 years. So if you go back in the past, you see that the CO2 concentration has shown, according to this measurement, this estimation of a measurement, large variations. It has gone down to about half, almost half of the concentration that it is today, has gone up, has gone down, has gone up, has gone down, has gone up, has gone down, has gone up, has gone down. And down here is from the same ice core, so measured in exactly the same location, just one location. But anyway, for CO2 this may be quite representative because we assume that CO2 is a very well mixed gas. So on time scales maybe of a yearly mean or a few years mean, this gas will mix very efficiently around the globe everywhere. So we assume typically if you do modeling, you have just one value of the CO2 concentration and not a value everywhere because it's very efficiently mixed, this gas. So this may be representative for the whole globe, actually, on this time scale at least. There are variations, but on very long time scales, these gases will be very well mixed. On the other hand, here's the temperature. And the temperature is really the local temperature because we have an idea already from our personal experience that temperature is varying from one location to the other. So the temperature here is really valid for this location. And so if you look at the temperature, also the temperature now, fortunately, in Celsius, or Kelvin if you want, if you look at differences, is the same. So we are better able to interpret this. The temperature nowadays, in the nowadays climate, is relatively warm in that region, but was very cold before, and then has also these kind of oscillations. Can you, if you see these kind of oscillations, let's call it oscillations, although from a real physical perspective you wouldn't call this an oscillation, but there are variations that seem to have some periodicity here. Can you guess what these are? What these variations, these strong variations represent in the past? These are the ice ages. So small changes in the parameters that regulate how the Earth is rotating around the sun and how the Earth's axis is wobbling a little bit. Small changes of these parameters change not really always the average radiation the Earth gets, but how this radiation is distributed from the pole to equator, or how this radiation is distributed from summer hemisphere to winter hemisphere, and so on. And small variations of this, people have made theories how to explain. It's essentially mostly related to the growth, the very slow growth of the ice sheets of the Earth, that they grow on time scales of hundreds and thousands of years. And people have made theories that relates these small changes in the parameters to the ice ages. And these temperature changes would be one of the periods that is actually forced by these changes of these parameters, how the Earth rotates around the sun and how the energy input is varying by small changes in these parameters. But the point that we want to make here is actually that if you compare these two curves, would you say they are correlated? They look correlated. From this perspective now, it seems we have enough degree of freedom, even by just raw looking at the data, not doing a correlation analysis. I guess if you correlate these two curves, you would find a correlation of 0.8, 0.9, something like this. But even just by eye, any physicist would say, yes, there must be some connection between these two. So this has been a very strong, in the recent years, a very strong argument also by climate scientists that say, okay, look, this is now worrying because if we increase the CO2 concentration, history has shown that then the global mean temperature, we cannot say this here because it's just one location, but you find similar curves on other locations, also in the oceans, made from estimates from coral reefs that are also very old and things like that. So people believe that this curve is valid globally. So there seems to be some correlation between global mean temperature and CO2 concentration. So that's the statistical proof that we have. Although we still have to be careful because so far, kind of the suggestive argument is that CO2 concentration causes temperature change. But so far, we don't really know. It could also be that these two curves are correlated because temperature change causes CO2 change. We will look at a figure later on that kind of also suggests that there is also a mechanism why a temperature change would cause some changes in the CO2 concentration. But still, it's still worrying that humans continue to burn fossil fuel, which is good because we develop. But on the other hand, it's worrying that by this we increase the CO2 concentration by our industries and things like this. And yeah, we may push the Earth into a climate which maybe have dangerous consequences. So this is the kind of the statistical proof that these two things are related, at least. Yeah, so here just, we don't want to go through reading this, but obviously the consumption, here's an example for the United States because the author of this book is from the United States. What's the fossil fuel burning? So in the United States, it's 40% oil, 25% gas, and 24% coal. And there's nuclear energy. Nuclear energy wouldn't cause any greenhouse gases, or at least not as much as the others. But as you also well know, may have other problems. Now, let's start to talk about more about these greenhouse gases and maybe try to get some physical understanding what's going on. Now, first we want to look at this graph here. Okay, this is again related to the carbon cycle. So before we mentioned that, yeah, carbon dioxide and temperature are highly correlated in the history of the Earth. But the carbon itself is a very complicated cycle. So there's something that people call the carbon cycle, because carbon is important as a greenhouse gas, and we'll try to explain the physical mechanism of this in a minute, maybe. Is a very important greenhouse gas in the atmosphere. But carbon is also present in the ocean and is permanently exchanged with the atmosphere, because microbes are growing in the ocean and using up CO2, and then the ocean is absorbing the CO2 from the atmosphere and so on. And so there's a very complicated exchange between ocean and the atmosphere, but also very obviously between the land surface and the atmosphere, because trees that are growing are converting carbon dioxide into oxygen. So there are very complicated exchanges also over land. And then there's our work where we dig into the oil and gas deposits that are there and burn them. So that's our small contribution. I would say the fortunate thing about all of this is the thing would be very worrying, because as we discussed in the very beginning, many million years ago, maybe the atmosphere was almost completely consistent of CO2 and almost no oxygen, because then the growth of the plants and of animals has caused this deposition of the carbon that is not anymore in the atmosphere, but is then deposited. And the positive thing about this, if you look at the storage here, is that oil and gas deposits, the units here are this kind of probably millions of tons or whatever, but it's only important here, the relative magnitudes. If you look, this number is 300. So as much as we can get kind of from the ground into the atmosphere is this number 300. A much larger number is stored in marine sediments and rocks, which we are not able at the moment to at least to burn them and to use them as a fuel. So even if we burn everything that is there, it will not be the case that we have an atmosphere again that is completely made of CO2. So we cannot reverse the process that the Earth has undergone in the last millions of years. That's the good news. So whatever we do, whatever the development is, we will only be able to burn, and that will be also very difficult already, these 300 units, which is much smaller than this number here, 100,000 times smaller than the CO2 that is kind of the carbon that is stored in other sediments that we are not able to use. So that's the good news. But still, we will discuss now why a greenhouse gas is so relevant for the Earth. Yeah, and then for the ocean, just to discuss this, why the ocean is important. The rule is that the ocean is absorbing carbon. So this is kind of a map of the CO2 flux at the ocean surface, and blue is negative here, and red is positive. So negative means that the ocean is absorbing CO2 from the atmosphere, and and red means that the ocean is giving CO2 to the atmosphere. So as you can see, there are these northern cold regions. In these regions, the ocean is absorbing CO2, and there are other regions, mainly the warm oceans, where the ocean is giving CO2 to the atmosphere. That means that in the ocean, the transport of mass kind of redistributes this on very, very slow time scales and has this cycle. So the ocean is important in this. You cannot ignore the fact. You cannot just assume, okay, CO2 is important in the atmosphere, therefore we have to model the atmosphere. No, you have also to try to model, if you want to make predictions or estimates of future climate, you have to make estimates of the movement of the CO2 in the water. So that's very important. Yes?
We have data for the temperature when the atmosphere of the Earth is full of CO2.
If we have data from that period,
Yeah.
it's again like proxy data, yes. Some very crude estimates, and probably if you go back to those time scales, in fact, there's almost no data anymore. Maybe you have just one measurement somewhere. So the data is very scarce, but yeah.
We can know the peak and
yeah. The Earth may have been boiling. I think it will be very difficult to get reliable estimates of the temperature, measured estimates from that period. But what people also do is you look at other planets, because there are planets around which have a similar atmosphere, similar physical behavior, maybe not CO2, but made of some other greenhouse gases. And you can maybe with satellites now measure the temperature there. And then you say, okay, maybe that has been the climate on the Earth also in that period. So that would be probably the way. Because going millions of years back, then it's very difficult to make any reliable estimates. This was not the right thing to do. This is what we have done. Oh, no. Let's go here. Oh, we kind of skipped this altogether. Yeah, nowadays is probably anyway an important discussion. This is a map of the observational network that is actually currently used to produce temperature measurements. So even nowadays, from actual measurements done by instruments, thank you. Yeah, there are regions which are very heavily measured, but over the oceans, obviously, it's very difficult. So, and use this somehow, this input kind of to make an estimate about the global temperature. This is a graph that shows the amount of measurements that goes into some estimates, some global estimates of surface temperatures. And you see here what we mentioned before. From the 1850s onward, there are some observational data, and then this amount has gone up. There's been some variations in this, mainly because of wars, actually. In war times, the observational effort has gone down a lot, obviously, but afterwards it has picked up. And the observations, the ground observations, are nowadays mainly replaced by satellite observations. So from the 1980s onward, in the beginning, it was still very difficult to make estimates from satellite observations of the Earth in the various bands on the ground temperatures and on various atmospheric fields. But nowadays, these algorithms are very good, very clever. And it's so from the 1980s onward, the coverage that we have for measurements are very, very, very good. So for 30 years now, more or less, we have a very, very good estimate of what is the Earth climate. So that's probably this increase that we see here in the last years. Whereas before it was ship measurements and other measurements that has been used to estimate things. Okay, yeah, here was just this explanation. Okay. We've seen this. This is the same. Okay, we should mention this. So what are greenhouse gases? What are the greenhouse gases? We have to name them. Carbon dioxide is a very important greenhouse gas. We still have not discussed exactly how they work. We will do that in a minute. But you should know, and this is very important, and don't get confused about that the absolute dominant greenhouse gas and the most important greenhouse gas is water vapor. Simply because it's very efficient, but it's also the quantity of it is much larger than the quantity of CO2 in the atmosphere. So water vapor can vary up to, let's say, from 0 to 5%. But it's a very, very, very efficient greenhouse gas. And it says here that from the 33 degrees of warming that we have at the surface due to these gases, greenhouse gases, most of it, 30 degrees, may be due to water vapor. So water vapor, that is very difficult for us to influence. We influence water vapor, of course, because our aspiration exhausts water vapor every time we speak, and we sweat and we use water. We influence water. But the exchange, for example, at the ocean surface is so much larger than what we do that our contribution is really too small to be measured. But if water vapor changes in the atmosphere, that has a big impact. So could be potentially a big uncertainty if we want to understand climate change, because water vapor in the atmosphere may change. And it's actually a very important positive feedback mechanism. And that's very easy to understand. We will probably also discuss this in more details later. But you can immediately understand this. We have discussed that the Earth is essentially heated by the sun. And most of the energy of the sun goes directly to the surface and is absorbed by the surface. Mostly by the ocean surface, simply because there's more ocean than land surfaces. At the ocean surface, we may lose heat by radiation, but to a large amount, we lose heat also by evaporation. So you can imagine that if we increase the energy input at the surface, we increase the evaporation, which means we may change the water vapor in the atmosphere. And people have made estimates. So if we increase the CO2 concentration, for example, we can estimate that the temperature will increase at the surface, and that will cause also an increase of the water vapor in the atmosphere. And this means we increase the temperature further. So we call this positive feedback. So the greenhouse gas temperature causes immediately a positive feedback mechanism, because increased temperature will cause an increase of the water vapor immediately. And that's a very, very strong positive feedback. So probably without the water vapor, the increased greenhouse gases would not be so dramatic as they are, because we also increase the... So water vapor is very important. Then there's carbon dioxide, which is so important because humans are causing a large increase. And there are other gases. The one that is named here is methane, so it's and some more gases actually, as you can see here. Even tropospheric ozone. So the ozone is very small amount because ozone, as you may have heard, is more important in the stratosphere where it absorbs the UV, ultraviolet radiation. But there's some small amount in the troposphere, and even that is a greenhouse gas. So the problem is more complicated, but scientists believe that the most important for concerning the human influence is the CO2, actually. But you cannot ignore the others if you want to make estimates of changing climate. Yes? This one? This one? This?
Yeah, over zone interval, it does not go very up or very low, causing this cloud.
Fortunately for the Earth, maybe. I mean, I guess this is a very good question. Why? I mean, the variation is between, let's say, a factor of 2 between the minimum value and the maximum value, at least in this period. Of course, if we go back millions of years, when the atmosphere was almost made of CO2, there would be probably a factor of thousands or hundreds of thousands. So it's a very good question why this is such a nice kind of robust behavior that it doesn't change so much. My answer would be the same as what we said last year. Somehow the system has existed so long time that it's in some kind of equilibrium. So there are positive feedback mechanisms that have we discussed before, but there are also, fortunately, many negative feedback mechanisms. So probably there are enough negative feedback mechanisms that if the CO2 concentration starts to increase too much, then the negative feedbacks will push in and will cause a decrease of this. But in principle, it's a very good question. Why has the Earth, and many people have asked this question actually also, why has the Earth climate in principle been so stable over maybe 100,000 or even millions of years? Quite stable, actually, since we have the cooling off from the production of our current atmosphere. Since that's the case, the Earth's climate is very, 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 very stable. It's really some kind of miracle, if you want, a miracle of the Earth. In fact, there are some theories. They're taken seriously, but scientifically, it's probably very difficult to prove that claim that the Earth kind of acts as an organism. So it has some kind of regulatory behavior. If the climate gets unsustainable for example, animals and vegetation, then the vegetation will adjust in such a way to make the climate again pleasant for them. So the Earth is kind of like our living organism. When we have problems, our body has problems, we get a fever in order to cool down the inner temperature of us. So kind of their hypothesis, this is actually called the Gaia Hypothesis, that says, the Earth may be something like a living organism. Maybe there's some truth to it, but there's no real physical proof. But kind of these curves, suggest there are at least so strong negative feedback mechanisms that avoid that, okay, these two curves are correlated, so when one is going up, why do they not go up in infinite? Is it just, or is it just the periodic forcing that is causing these variations, and these just follow? It's a very good question, I think, in principle. But I think the answer again is that the system is in some kind of equilibrium, and the fact that it has survived over millions of years probably means that yes, there have to be enough negative feedback mechanism in the system for it to be relatively stable.
Okay. Would we also say that because you say that once you increase the temperature, once you increase CO2 concentration, the temperature increases, and so there is evaporation, there is more water vapor.
Also, yes.
Will we also say that the water vapor can go into the formation of clouds, so that instead of having a positive feedback, we have a negative feedback? That is, the temperature will reduce.
Yeah, that's a very good. So you think about already about mechanisms of climate, of the dynamics of climate change. Yeah, this is a very good point actually. That is even discussed by climate scientists. Yes, this is one of the other very important things. Yeah, probably the first order mechanism of water vapor is a positive feedback. But then the cloud formation, exactly as you say, can act, which is related also to water vapor, can act as a negative feedback. Can act as a negative feedback. Because, again, it's very complicated. There depends which level the clouds are, actually. Typically, I think on average, low clouds act as a negative feedback because they reflect the sunlight then just before it hits the Earth's surface. So very low stratus clouds, they called. They are usually considered as a negative feedback. High clouds are often considered, if you do the complex calculations, it turns out, act more likely as a positive feedback. So even there, it's not clear, not 100% clear what's happening. But that's a very good point, actually. So everything is, it's not an easy problem. But models try to include all these effects. In the end, anyway, you have to try to understand what even the models are telling you by making budget analysis. So what is the change of CO2? What is the change of water vapor? What is the change of cloud distribution? And so on. So it's a very important point. Yeah, very, very good point.
Can we predict from this graphic like a period of ice age?
Yes.
I mean, because it looks like we are close to one.
Yes, we are close to one, actually. We are at this time scales. We kind of are close to one. I think the next ice age is the next close ice age. Well, close to one means, I mean, at the moment we are just well in the warm period, as you can see. And fortunately, typically, it's more the change from warm period to ice age is more gradual. Not always, but can be quite quick sometimes also. But yes, I think it's in the next 50,000 years or 30,000 years, we would probably go into the next ice age. But even there, climate scientists some climate scientists claim that our increase of CO2 may prevent the next ice age to happen, actually. So if we cannot kind of adjust our behavior and the CO2 will increase as much as is predicted by most of the scenarios that scientists are doing, then this increase may prevent the next ice age to happen. And that would be quite... I mean, we don't care really so much about it because it's 50,000 years still to wait. Most of us do not care.
The real correlation between the temperature and carbon dioxide, right?
The real correlation?
So how do we know? I mean, we don't know. Okay, from this graph, we can't say nothing about which is the cause.
Yeah, no. From this curve, this is correct. But we will discuss in a minute that we have physical arguments how greenhouse gases act. Actually, from these curves, also we cannot yet say what is causing what. But in principle, yes, we go into the next ice age potentially.
Global warming is not a trait at all, I think.
Global warming is not.
It's right. It's just a cycle, and we cannot control it. I mean,
That's what you are saying.
yeah. I mean, whether we burn mud fuels or whatever we use is not. I mean, we cannot. It's just a cycle. I mean, it's just a nature.
That's an interesting opinion, but as I told you, I would say 90% or 95% of climate scientists would think that it's a big problem what we are doing, and it may influence these cycles. Yeah, you're right. This looks like they're just cycles, but as I told you, climate scientists believe that actually our behavior may prevent from the next drop to happen.
Yeah,
So.
because I asked you the question that if we have the data for the temperature in the past when the carbon dioxide is like full in the air, then we can see the peak, and then if we had something like this, then okay, we can be sure that there will be ice age, because now the content of the carbon dioxide is not too much like that we had in the
Okay,
past.
yeah.
So
No, in that period there was no. Yeah, that's okay. Yeah. No, you are absolutely right. Okay, This is a very good point, and I don't think we have a graph here, but there you will find graphs on the internet, but more or less I know how this curve looks like. Yes, it's a very good question. So if you go back, let's say, I don't know, millions of years, 2 million or probably more. Probably more. I have to. I'm not very good in paleoclimate things, but essentially, what has happened is the Earth has cooled off for a very, 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 very long time, and this cooling off has gone along with a decrease of the CO2. So there's the production of oxygen by plants, by sedimentation of the non-eroded stuff has gone on for millions of years. The temperature has been. There are proxy estimates that tell us this was the case. Has gone like this, and at some point there was no, according to those estimates, there was no variation, no ice ages. At some point, when the temperature became, so to say, cold enough, then the variations in sunlight was enough to cause these kind of ice ages that we see in these curves. So that was what has happened essentially. And the CO2, this is temperature and CO2 if you want, both have undergone the same kind of behavior. So it's only from the point on where the CO2 concentration had the levels that we see there, and the temperature were on the similar level then, that the changes in ice ages are visible. Before there was just this slow drop in temperature, it seems, from paleo studies. So the story is a little bit more complicated than that, actually.
why so we care about the CO2? The temperature and the carbon dioxide only. We have I don't know how much the effect of those gas really is, but
Yeah. We will. There must be a. I sometimes get lost in this on this web page, but let me see. If we see that here. Okay, this is a. We should probably, as we discussed this already now, this is a. No, I think we should go and discuss things from the beginning. So this is kind of a picture that is often used to explain how greenhouse gases work. So essentially, as we said, the sun is our main driver. We have to have energy input from the sun. Most of it goes to the surface, not everything, because there are clouds. Some is actually absorbed in the atmosphere from the sunlight, but most of it goes to the ground. Then the ground somehow is absorbing it, heating up, radiating, evaporating, and does other things. Obviously, if there was no atmosphere, then everything would go straight out into the skies. But one of the arguments is how greenhouse gases work is that since they are, and we will see this in a minute, they are efficient in absorbing these long-wave radiation, not the short-wave radiation from the sun, but the long-wave radiation that is radiated, according to the Stefan Boltzmann law, from the Earth's surface. They are efficient in absorbing this radiation. Then it's absorbed and radiated back again. Absorbed and radiated back again. This is the reason why the surface heats up when we have greenhouse gases in the atmosphere. Actually, there's an explanation that I like much more than this one. This is one of the explanations how greenhouse gases work. But I think the simpler explanation, you can see this, right? Even, can you see this? Or should I put on the light? You can see. Okay, in the end it was R equals sigma T to the power of 4. Annual mean incoming absorbed radiation at the surface, on average, has to be balanced, a black body, by, maybe if it's not a black body, sign epsilon here, by the Stefan Boltzmann law. So this temperature essentially will not change if we do not change the incoming radiation. So this number is about 300, maybe 300 watts per square meter on average. Maybe some other number, but not much difference. And that gives us this temperature to be about 255 Kelvin. That's the radiative equilibrium temperature of the Earth. That's minus 255, that's almost minus 20 degrees, minus 18 degrees. Okay, that's what we mentioned before. If the Earth, let's say that's the Earth, and that's kind of the atmosphere around the Earth, which I just draw schematically as this. If the Earth doesn't have an atmosphere, then this temperature would be the temperature at the ground, because the ground is what is radiating away. That would be the Earth's surface temperature, minus 18 degrees, without greenhouse gases, if we want. So this would be even valid if there was an atmosphere, but no greenhouse gases at all, because they would not, the atmosphere would not interfere at all with the radiative equilibrium. With an atmosphere that contains greenhouse gases, this is not the case anymore, because the atmosphere is optically thick. So it's not anymore as if there was nothing. So this temperature of 255 degrees, as a consequence, is not at the surface, but at some point above the surface, which is typically, in our current climate, about maybe 5 kilometers. So at 5 kilometers, we have typically this temperature, on average. Now comes the question. At the surface, it's warmer. We know that. At the surface, we have an average temperature of something like 13 degrees, I think, average. So the surface is much warmer. So why do you think is the surface warmer than this temperature? So this temperature moves up. That's for sure. And therefore, the temperature at the surface is not necessarily the same as this. And in fact, it is very different. It is much warmer. Why is the surface warmer than the temperature on some outer level of the atmosphere? Okay. Make estimates. Because the greenhouse gases is an obvious and true answer. But so why? But still, there's physically. I mean, this is just restating what I said here. Why is it colder when you go up on a mountain? Typically, not always, but typical. That would be probably also be valid even without greenhouse gases, actually, that fact. And the reason is simply there are two parts of the explanation. The first and immediate clear is that our planet is heated from below, essentially. Most of the solar radiation hits the surface is heated up, and then the heat is distributed in the vertical. But most of the direct heating is at the surface. That's one explanation. If you want to know actually the rate with the temperature changes with height, you can do that quite accurately. The number is, it's almost like quite accurately, not 100%, but a good estimate is that the temperature change with height is about 6.5 Kelvin per kilometer. 1 kilometer. It's and this number is quite a good estimate. And can you guess why we are able, or if close to the surface, it's even very close to 1 Kelvin per kilometer. So, can you make a guess how we can estimate this? Yes. So here now comes the first law of thermodynamics. Whenever we have a parcel that is near the ground and we move it up, we have two ways of trying to explain it from physical principles. One is the really internal energy way. If we move a parcel up, there's more space, so it expands. And if a parcel expands according to the first law of thermodynamics that you all know from physics, it has to cool off if we do not produce any heating on it. The other explanation is the enthalpy way, that if we move a particle up, we also know the pressure decreases. Everybody knows that if we move up, the pressure has to decrease because the density of the particles becomes less. And that also, for the same reason, causes a decrease in temperature if we do not heat it. So these numbers can be estimated from that principle. So we would have to write down the equation: change of temperature with time equals to minus p, the divergence of the velocity, essentially, plus then q, the heating. And the heating would be obviously, for example, by greenhouse gases. But these processes are assumed, if we really move up a parcel, are assumed to be much more efficient to govern the vertical temperature distribution. So that's the reason why, given that we have greenhouse gases, then that the surface has a larger temperature than this thermal equilibrium temperature, which exists at some level, which can be estimated. So I think that is the best explanation for the fact that if we have greenhouse gases, then our surface temperature must be warmer than the equilibrium temperature according to this equation. So greenhouse gases are important in this respect. And yeah, so here's just an picture. So they obviously they absorb and they radiate away. They are also in equilibrium. But I think this figure is probably interesting to look at. So here's according to wavelengths. It's in meters here, the units, and here's a nicely estimated. So this is the infrared, this is the long wave, and this is the visible where we can see, and this is the high frequency, more high frequency part, the ultraviolet part. And if we go to our greenhouse gases, so here is so first of all we know that if we take the atmosphere as a whole, obviously in the visible band there's no absorption. That's the reason why we can see in the visible band almost no absorption. But in all the other bands it's not like that. So thank God, the oxygen that we have in the stratosphere is very efficient to absorb the high energy ultraviolet radiation that otherwise, if it hits us at the surface, would be extremely damaging. Therefore, the ozone hole that has been discussed also in the past is very dangerous because we may, if we remove the oxygen and ozone from the stratosphere, then this radiation may come to the ground and may hit us and may cause severe diseases, and it's very damaging for us. So this is very good. On the other hand, it's also very good that we have in the long wave that the atmosphere is not transparent. The atmosphere is not transparent. It's not uniform as in the shortwave band, but it's like this. And the gases that are contributing here most efficiently is water vapor and carbon dioxide. And of course, it depends, however, on the quantity of these gases, how efficient they are. And the reason why water vapor is more efficient than carbon dioxide is also because it's absorbing just more efficiently, but it's also because its quantity is much larger than the carbon dioxide. So the carbon dioxide has these few bands where it's efficiently absorbing the long wave infrared radiation that the Earth is radiating away. Therefore, we have to have this effect. So this is the physical explanation why, if there's a greenhouse gas, we have to have, if we increase greenhouse gases, the surface temperature should increase. As a simple back of the envelope calculation or of a thumb rule. Then of course you have to use models to make more quantitative estimates of this.
Okay, I don't know, but this is my view. Okay, when we see the plot, we have some fluctuations, and then if we care a lot about our Earth, like to minimize the carbon dioxide, okay, we may go into the ice age, and then we may trap there for the whole. I don't know, and then we'll never come back to like those. And I mean, it's not global warming the only threat, but we can also be like trapped in the ice age, and then we'll never see like light, and then I don't know, but it's just.
So you're saying if we do too much to remove carbon dioxide, we may be trapped into an ice age.
And then we'll never come back to like.
Yes. Very a little bit hypothetic, I would say, because if we look at projections of carbon dioxide, there's none that goes down actually. They all go up, and then if this.
Yeah, it looks like a metastable state. It's just fluctuating, but sometimes, even when we study some physical problems, okay, the curve is not always smooth, but we have locally some fluctuations.
Mm-hmm.
And sometimes, okay, we'll have some local stable state, and okay, sometimes we can stay there forever, and maybe it will happen go to in the ice age, and then maybe we can be there forever, and we can trap there. I don't know. It's just.
Actually, there has been a period. Many papers are written about that, about the Snowball Earth. There has been a period where apparently an ice age was so strong that the whole Earth was covered by ice. And you know, the mechanism for ice ages is essentially, the main positive mechanism is that if you increase the ice cover, you reflect more sunlight. So if the whole Earth is covered by ice, then the sunlight variation doesn't matter anymore, because anyway, anything is reflected. So it's a positive feedback mechanism. That's the positive feedback mechanism people think for ice ages. That if you have variations in sunlight that make the ice grow, then this growing ice will reflect even more sunlight, and we go into an ice age. And usually these ice ages have been such that some parts of the globe were covered by ice. That was the equilibrium. But apparently there was at least one ice age where the whole planet, even equatorial regions, were covered by ice. And people have done, of course you cannot measure these kind of things, but people have done simulations with model, try to understand how did the Earth get out of such a state. People have tried to find mechanisms how that wasn't stable forever, because in principle it should have been stable forever. But there are complicated things, melting at the ground and maybe dirt at the top. I don't know all the explanations, but there are mechanisms proposed how the Earth at some point could move out of such a seemingly very stable state. But people are researching about these kind of things. So it's good that you think about these kind of. It's very complicated, and it's by no means straightforward. But if we are talking about climate change, actually we are not talking about the next 50,000 years, but people are making estimates, and we will discuss this probably at the end of this lecture, maybe up to 100 years, 100 years. And keep in mind, the estimates that the realistic estimates, and they are not exaggerated, that people are doing is that the CO two in 100 years may have doubled, or may have even, in worse scenarios, maybe are 3 times as much as they are nowadays. And compare that with the climate history. It never happened before. Never happened before. So it's a very unusual state. So that's the worrying part. In a very short time that you wouldn't even see on those long-term graphs, humans are supposed, if we do business as usual, to double or make the CO2 concentrations 3 times as much, which has in the last million years not happened. So we have to go back really to the curve that I drawn before, far back in the Earth history to find where there were no ice ages at all, actually, which is one of the explanations why people think ice ages may vanish if we go, if at some point, so this is the situation, the Earth had cooled off, and at some point ice ages appeared. So if we go up too far here in this curve, maybe no ice age may happen anymore. So they are strong, I mean, it's good to be critical about this and to think, but there are very strong physical arguments that this could be a big problem. Already in the next 100 years, that's the problem. And then the system is by no means, as you can estimate, in 100 years or even 1,000 years, we can estimate about the CO2 concentrations and about the temperature, because the temperature adjusts relatively quick according to our models. But the system is still by no means in equilibrium. So you will need to wait another 10,000 years to find the real equilibrium response of the system. Models are at the moment not really able to do this. But we kind of with models we can estimate what's the tendency for the next, for scenarios. If the CO2 concentration is this, what will be the response of the Earth? But still, by no means the Earth system is in equilibrium then yet. So yeah, this curve has been taken as a kind of warning that maybe if we go up too far here, we're in trouble. We're in trouble, maybe not in trouble, because it's good that there are no ice ages anymore for economy. Or not everybody is in trouble. In fact, there are some studies on global warming that, of course, you find regions that profit from global warming. You may be able to produce wine. At the moment, the wine producing belt is kind of some subtropical belt. The Mediterranean, our region is in it. It has to be dry, but not too dry and warm. So this belt extends over the Mediterranean to China even, and in the southern hemisphere also, Australia, South America, and South Africa. And this belt, with global warming, with climate change, will expand probably to the north. So perhaps in 100 years' time or 200 years' time, England and Germany or Scandinavia will be able to produce good wine, which has not happened in the past. So this is not all negative anyway, but there are other severe problems, of course. Oh yeah, just some other errors. There are some other things that are important, of course, for climate. One, for example, is aerosols. So this, you cannot see the border, but this is Africa here. This is here are the Canary Islands. Where's Africa? I don't even see it. But this is a dust storm coming out of the Sahara. It's beautiful. You can see this from the satellite. And this, of course, something like this has a radiative influence on the Earth. So this would cause perturbations in the local radiative balance in the Atlantic Ocean. You can even sometimes, when it rains in Trieste, you find dark red particles on the cars. That's typically dust from the Sahara that has been transported up in the cyclones, and then if it rains out, you find this dust. So there are other climate effects that are important and nice to model. Okay, we have been here already. We've been discussing this already. I think I want to a little bit, because this goes into the discussion that you have been initiating. So there is this. Yes, one more.
Okay. In which region is the water vapor high?
The water vapor, yeah. So okay. So this is another important thing. So air and water vapor can be in equilibrium only at a certain pressure at a certain temperature. So if at some point the temperature becomes too low, the water vapor cannot be in a vapor state but has to condensate. This happens in clouds. And clouds are typically, as you know, from looking outside at some higher levels. So that means as the water vapor rises up in some convective event, particle that is heated at the ground, moves up, cools off because of this law, then the water vapor at some point cannot be in equilibrium anymore, but has to condensate and releases the heat. Now, that means, this law kind of means that most of the water vapor that can be in water vapor state has to be at the ground, at high temperature. So the water vapor amount can be in the air is a function of the temperature and of the pressure. In most of the water vapor, you would have at the ground where we have high temperature. And then it decreases with height. Simply because of the fact if we go up, it has to condensate. So we lose the water vapor and it transforms into liquid water and drains out. So we cannot have much water. In the stratosphere, there's almost no water vapor anymore. So it's mostly trapped to the ground, which is very different from CO2, which is also in the vertical quite well mixed.
So the driest continent is Antarctica.
Yes. If,
So we don't have water vapor there.
essentially, yes.
So,
Yes. Where it's cold, there can be no water vapor. That's, but even small, no water vapor is not quite true, because much less water vapor.
yeah, but compared to the other continents,
Yes.
it is small.
Yes. Yes. Okay, so we have this. Yes.
Is it possible for these climate changes to occur in certain parts of the
In certain parts of
Earth?
the Earth. Yeah, of course, what we are looking at now, this is the global mean, kind of an estimate of the global mean temperature. You use models. Our models are, of course, grid point models. So we have an estimate what will be the climate change regionally. But to answer your question, the climate change, when you change something, at some point it will influence the other points. So climate change is a global problem. But there may be huge differences from one region to the other. So it could well be, the typical situation is that you warm up more in the polar and extratropical regions than at the equator. There are several hypotheses for why this is happening. So, for example, if you double the CO2 concentration, the typical answer we get from climate models for the reaction of the temperature to that is maybe a 2 degrees warming in the tropical regions everywhere, with some small changes, but more or less 2 degrees. And then as you go to the extratropics, you may find 8 or even more degrees. Also depending a little bit on the ice melt, because the ice melt then has a very strong positive feedback on this. So the answer is no, you cannot have a regional climate change only. But you can have regional modifications of climate change. I mean, what I'm talking about now is only temperature. For example, rainfall, which is very important for us, for agriculture and for many other things, for drinking water resources. Rainfall changes in a much more complicated way than the global mean temperature in these kind of scenarios. Maybe we can have a look. Well, this would be just by chance if I open another window. Maybe this will take too long. Report. Maybe summary for policymakers. No, there's nothing inside here. Probably very big document, but let's see if I find some map of global temperature changes that are Since there are no figures, no. This takes too long, I think. No, this takes too long. Sorry. Next lesson, I will try to find some nice plot that shows us what is the regional estimates of if the CO2 concentration maybe is doubled or so. You will see it's not a uniform pattern, but for temperature it's still quite uniform compared to other climate parameters, which are probably even more important, like rainfall. Rainfall can change in a complete... It's not said that in a warmer world everywhere there's more rainfall. On the contrary, there are many regions that have less rainfall. And so yes, climate change can be regional, but you will feel the change everywhere. So you cannot restrict climate change to a region because the physical laws will carry the signals all over the globe. That's the short answer. Oh, yeah, to discuss this was the... So there are ideas. If we cannot keep economies and industries from growing, then obviously the CO2 concentration is bound to get up and has this doubling or 3 times values, which we think for physical reasons is a big problem. So can we do something else against this? Can we remove, maybe by other means, the CO2 from the atmosphere? Because we know the carbon is a cycle, so it's kind of absorbed by the ocean, absorbed by plants and things like that. So is there a way to remove the CO2 from the atmosphere by other means? So we continue to blow it out, but we kind of more efficiently, there are other possibilities. There have been proposals. There's this iron hypothesis. Some scientists has claimed that if you throw iron in the ocean, then bacteria are much more efficient to produce, to absorb carbon. And he has actually made some experiment that shows that this could be the case. This whole field of trying to remove the CO2 from the atmosphere by other means. So another hypothesis is that you could kind of try to increase the absorption by land surfaces, by increasing the soil that contains carbon and things like that. This whole area is called geoengineering. So at scientific conferences, there are now always sessions on geoengineering. So you make some kind of hypothesis. What could we invent, given that economies will grow? There's nothing we can do against an increase, and our main energy resource remains fossil fuels. So what else can we do? And some people invent things. They are much. These would be actually still quite, I think, potentially reasonable solutions if feasible. There are other solutions. There are things that have been proposed as putting mirrors on satellites in the skies to reflect sunlight. Or you can imagine that potentially, of course you cannot test these things in the real world, you can test these things in the model. As you can imagine, you may adjust the temperature to be more or less the same, because you may, if you change the solar radiation and you change the greenhouse gases, maybe in the end you get a similar surface temperature, but you may change other things, like temperature profiles or so. So geoengineering is very interesting, but before actually humans are going to do it, they have to be very, very sure that this is not causing any other damage that is much worse than having a CO2 increase. So, but this is the whole field of science, with modeling, to have some ideas which you could implement in a model. Reducing solar radiation in a model is very easy. There's a parameter, solar constant. You change that. You reduce that. You increase CO2, and look what's the result. If you trust your model and it gives nice results, then you maybe could think of making a real experiment, but I wouldn't trust the model in this case. I will not talk about the food web because I don't know. Yes.
Okay. Can we also say that we can? Okay, if we increase more vegetation in the by planting more trees, we can also decrease the carbon dioxide because trees use the carbon dioxide.
Yes.
As a product.
Yes.
So
if you increase the amount of trees that is permanently there, you will trap more carbon, because that would be a simple calculation. The amount of carbon that is trapped in the vegetation is the amount of wood that material that is there. If you increase that amount, you will absorb an equivalent amount of CO2 from the atmosphere probably. So that's a kind of a safe bet. If you increase the amount of vegetation, you will reduce the CO2 in the atmosphere. And vice versa. If you remove trees, you will anyway increase even further. Well, if you remove trees and burn them, you will increase the CO2. If you remove trees and build things and avoid that the wood decays, you will not change the CO2 concentration. But yeah.
We will have more oxygen, right? When we plant trees.
Yeah, we will have more oxygen.
And having too much oxygen is also, I think, may cause a problem. I don't know.
May also cause problems. I have no idea, honestly. But here we are talking about, I mean, the numbers the changes we are talking about are important for CO2, but since CO2 is such a small amount, the variations in oxygen are really small.
Excuse me. I want to ask, are they calculating the rate of reversing the process? Because they are just looking solution for how to reduce it. But after we reduce it, at some point it has to be turned back. Are they calculating this rate?
No one at the moment is really thinking seriously to do any kind of these. Apart from the people maybe who are doing the research, I don't think any government at the moment is seriously considering anything like this. So this is really just hypothetical thinking. I mean, an easy way to reverse the process once you have removed something is just to wait that fossil fuel burning has increased the amount of CO2 again.
Yes, because my worry is if the rate is very small, there is no use of just reducing it. But if the rate is long, so it might be a solution.
Yeah, you can think about it. So the last point we want to discuss is not really discuss, but just tip on is abrupt climate change. Have you seen the film The Day After Tomorrow? Who of you have seen the film The Day After Tomorrow? Remember that film? It's quite nice, I think, isn't it? You remember? Where they were talking about an ice age because of there are some very few serious theories now, but some years ago that has been taken a little bit more seriously, that actually increasing CO2 may cause a very quick drop into a next ice age. Regional ice age, though, in the North Atlantic. So the claim is that, and we will discuss this, and this has happened in the past, actually. The claim why people saying this is because this has happened in the past. And here's a kind of a proxy, again, from proxy data, some kind of estimates from ice cores, from Greenland here in this way. So there was this is now thousands of years back. So when at the end of the past ice age, it started to warm up, in this region in Greenland, it started to warm up. And then there was a sudden, for thousands of years, a sudden drop back of the temperature before it recovered then to the state where we are now, essentially. So, and this drop was quite sudden. I mean, the recovery was also quite sudden. So people have wondered why this has happened. People have asking the question, why, what can be the explanation for such abrupt changes where it should have been, since it's going, the radiative forcing was just going from kind of cold to warm. So why was there this sudden change? And the theory is the following. The North Atlantic is a very special basin. We have seen that previously. Which figure I want to show? This one, I think. We have seen this figure previously. All ocean basins are transporting heat from the equator to the poles. And here with the change of sign, which is because the y direction is always 1, but the poles are opposite. Almost the Atlantic, because the Atlantic is this here. The Atlantic is always transporting heat to the north. So the Atlantic as a whole, the ocean circulation in the Atlantic, is transporting heat from essentially almost the South Pole to the North Pole, permanently. And the mechanism for this is called Thermohaline Circulation. So thermal and haline means salt. So the reason for this to happen is that cold and salty water is heavy. So the equation of state of water, essentially, tells us that if you increase the salt, you increase the density. If you make water colder, the water's highest density is 4 degrees about. So typically for our purposes, cold means dense because the average temperature is above 4 degrees. So in the northern Atlantic regions, the water is cold and quite salty because on the way to it there has been a lot of evaporation, and it's cold because we are in polar regions, and then this water is sinking down. And this sinking down in these northern regions causes this large circulation, this thermohaline circulation in the Atlantic that goes all the way down from South Pole to North Pole and up again. And people claim, just to make the story short, we will not discuss this too much, that during this period what had happened is, in this ice age, the North American continent was an ice sheet, essentially. The whole North American continent was covered with a huge ice sheet, kilometers more, several kilometers high. When the Earth started to warm because of the change of solar radiation, this ice sheet melted and the water flew into the North Atlantic. Now being ice, it's coming from rainfall or snowfall. It's a sweet water. So it diluted the salty water of the Atlantic, which is then less dense. So suddenly this circulation stopped. But suddenly so in this film they claim that for the purpose of the film they made it happen in 2 weeks or something. That's not realistic. It may happen in 100 of years or something. But suddenly this circulation stopped, and the circulation that is warming mainly the European region and the northern regions has stopped. And so they dropped into this next ice age.
What is that name? The younger something?
Younger dries is just the name of this period.
Okay.
It's just
Are such things possible
And you know what a hysteresis is? A system with memory. So somehow the figure of this is that you can have, if you have moderate changes of salinity, then the temperature in the North Atlantic will adjust smoothly. So it's a smooth system in the phase state. But if you reach a certain threshold, then the temperature, a small change of salinity, so reducing the salinity, the temperature may drop because you shut down the circulation. And then you cannot come back from the state anymore easily. So then you are you have two possible states with the same salinity, in fact. So in this state here, then the thermohaline circulation is shut off and it's very cold. And in order to get it back turned on, you have to increase the salinity a lot. So this is the hysteresis. You call this in physics. You know this from other parts. So people have tried to model this with climate models. Here's just what's happened in one case. This is probably so you call this ensembles. So they probably did 100 or 1,000 of simulations with slightly different initial conditions, and looked what is the possible future if we increase. Here's doubling CO2. So they do this experiment, what we have mentioned already several times, and they look what happens to this circulation. So if you look at this, most models say this, and this is a measure of the strength of this circulation. Most models say this is the current state. Then most models say there will be some oscillation. Then it will reduce a little bit, but will stay stable. There are a few models, as you can see here. Sometimes they turn off. So from this one, we say there's some probability this could happen actually. But you look at the time scales. We are talking about 1,000 years here. But then you see, ever so often there's a model that drops off to zero. So it's kind of an interesting hypothesis, but still, I would think let's say even if this happens, it turns off. It will probably not be an ice age because the mean temperature increase is so much that this would cause a reduction of the temperature increase. So if we have a 3 degrees warming on average, maybe this reduces it to 1 degree warming or 0.5 or almost 0 warming, but there will not be a strong cooling. This is the general